All right, so let's look at this kinetic molecular theory that we talked about in first semester, Unit 4, and we were looking at how gases related to each other. Now we're going to look at that in reactions and what happens with gases in reactions and how we can take measurements when we have a mixture of gases instead of just one particular type. We're also going to look at molar volume and how much 1 mole of gas is going to take up. So this is just kind of a little bit of a review. Back in Unit 4, we talked about particles of gas. They're always in constant motion. They move in straight lines until they collide with another particle or a wall. They have this elastic collision, so they don't run down. Their energy can be transferred or switched to another particle based off of how those two collide, but we never lose that energy. It's conserved the entire time. Then, in our theory, we say that particles do not stick together. Well, in a reaction, if we're going to react two gases together, when those particles hit, they will stay together. But again, we're looking at this theory of these little gas particles bouncing all over the place. Temperature and pressure, according to the KMT model or the kinetic molecular theory. Temperature, we've decided in the past that that's speed of the particles. Hotter the temperature, the faster they're going. The slower the temperature, the colder they are, or the slower the speed, the colder they are. When we take a temperature measurement, we're looking at the average kinetic energy or the average speed of all of these particles in a sample. Pressure of a gas is related to how many times and how hard the hits of the gas particle to the sides of the container, not to each other. So that's a big point that I want to remind everybody of. That pressure deals with hits against the wall, not hits in between with two separate particles. Now the frequency, how many times they hit, that can be changed by their speed. If we heat them up, they will hit more often because they're moving faster, or by the number of particles that we have in there. If we put more particles in, we get more hits. If we take particles out, we get less hits. The impact is only affected, the force of the impact is only affected by the temperature. Faster moving particles are going to hit harder than the slower moving particles. Okay, in summary, we kind of looked all of this over. Pressure and volume are the only ones that are inversely proportional. So if we make the container smaller, we cause more hits on the walls, and that makes pressure go up. So volume, changing the volume, making it smaller causes pressure to go up, making it bigger causes pressure to go down. But the rest of them are all directly related. So if we put more particles in, then our pressure is going to go up. If we take particles out, the pressure is going to go down. Or if we increase our temperature, the particles are moving faster, so they're going to hit harder and more frequently. That causes pressure to go up. If we cool it down, drop the temperature, we're also going to drop the pressure by making less hits, and those hits will be slower. And then it's the return of the lovely IFE tables where we have pressure, temperature, volume, and number, and we look at their initial states, their final states, and their effect, and then we can use proportions to work that, or ratios to figure out what our new temperatures or pressures or volumes will be. A little reminder that we have Kelvin needs to be in, our temperature needs to be in Kelvin. So if we're given a degrees in Celsius, we have to take that up to 273 Kelvin. We generally cross off the variables that are held constant because they don't matter. If they don't change, they're not going to affect our variable. And then we just use these factors to calculate. Here is a little example that I already have out for us. We have 150 milliliters, which is what we placed here initially, and it's at 25 degrees Celsius. You'll notice that in my problem I put 298 Kelvin. That's because I took the 225 and I added 273 to it to get 298. Then it's asking for what's our new volume. Our new volume, hence the the question mark there, and it says at 50 degrees Celsius, but again, we added 273 to it to get 323 Kelvin. Now, if temperature goes up, volume's going to go up. Based off of this arrow, we are going to multiply by the bigger number. So we're going to put 323 on top and 298 on bottom. So we take our 150, multiply by 323, divide by 298, and I get 163. So our little cute saying goes, the arrow shows where the big one goes, and we're talking about this arrow right here. We're talking about the arrow that is underneath the question mark. That's the arrow we're looking at to figure out where the big number goes. And in this case, it was 323. Our arrow was pointing up, so 323 went on top. Okay, enough about reviews. Now what I want to look at is if containers have more than one type of gas. So looking at these two boxes here, we have two containers of equal volume, and they're at equal temperature. Container A has 5 molecules, and container B has 10. So if we compare these pressures, A is going to have a lower pressure, and B is going to have a higher pressure. Okay, what happens if we put these two together? So we had 5 from A, 10 from B, and we put them together, and really we have 15 molecules sitting over here in our final set. But what happens to the pressure when we get over there and we add it? Exactly what you think is that in that third container, when we've put them all together, we've added A particles and B particles, and we've caused that pressure to go up. And it goes up by just adding those two together. Okay, so then with this, we can do some interesting things about, fractions of the gas A to gas B, or we can look at percentages. So let's look first. Okay, in the following, we have 1 atm for gas A, 2 atm for gas B, and then when we've combined them, we have 3 atm because we've just added 1 plus 2 is 3. So gas A is going to exert 1/3 of the pressure. So if we look at this atm, the gas A is doing 1/3 of the hits, whereas gas B is doing 2/3 of the hits. So the amount of pressure per gas is proportional to its fraction inside that container. Okay, how is this related to mole fractions? Well, we can make up numbers. Again, we have 5 moles and 10 moles, and then put them together and we get 15 moles. Looking at this, it still makes sense that there is only 1/3 of those particles in that last box that belong to A, that are type A particles. So 1/3 of the hits are coming from type A particles. Again, 1/3 is A and 2/3 is B. Just like what we saw with our fraction, or with our pressure. So gas A makes up 1/3, or 5/15 of the total moles, and gas B is 2/3, or 10/15 of the total moles. So what we see is our mole fraction and our pressure fraction are the same. This allows us to solve for one another. If we know what all the pressures are, we can figure out what the mole fractions are. This could lead into empirical formulas, if you remember from a while ago, and all of those. All right, so I want to look at molar volume and this R constant. So these are the last two things we're going to talk about. Molar volume, this applies to all gases. Doesn't matter what type, if we're looking at CO2 or if we're looking at something as small as H2. All of the gases in a mole will take up 22.4 liters if we are at STP. Okay, so if we're at STP, which means our temperature is 273 Kelvin and our pressure is 1 atm, of course we can change that to be 0 degrees Celsius because those are the same temperature, or we can change our pressure to being 760 millimeters mercury. And that is all, the same pressure, just different units. So at STP, 1 mole is going to equal 22.4 liters. What is good about this is that in lab, we can collect gases in a tube and we can read their volume. And based off of their volume, we can use 1 mole equals 22.4 as a proportion, and say maybe we ended up getting 13.3 liters. What is our moles? We can figure that out using this proportion. So it's very helpful in that way. We did briefly talk about this in semester 1 when we were kind of looking at the gas laws, but here it is a little bit more explained. And then we have what's called the R constant. So we have already figured out that pressure, volume, number of particles, temperature, all of these things are related. Well, they're related by this R constant. So what we see is that we have PV over NT equals this constant. And based off of that, if we know the pressure, if we know the volume, and if we know the temperature of our room, or of our condition where we do our experiment, we can use this R constant to figure out how many moles are there. And in stoichiometry, that's all that we're trying to figure out. Now in lab, we're going to look and we're going to see how close we can get this R constant to the true value, which is 0.0821 atm liters per mole Kelvin. So what this is our pressure, volume, and temperature, just like we have over here. This number does change based off of our pressure. So if I wasn't using ATM here, if I had MMHG or if I had KPA, those numbers would be slightly different. But I would give you those on the test if I was going to give you a different pressure.